Dr. Amaury Alvarez. He will speak about the joint work with Wanderson, Lambert, Dan Marchesin, and Bruining about the mathematical theory of two-phase flow and several chemical species, geochemical flow.
Okay. Good morning for all. I speak today the presentation that Wanderson prepared for us because he has some problem that to stay today with us. So I tried to explain this. He sent to us yesterday this presentation. So but I think it's important because in this work are obtaining nice results of a special kind of system of hyperbolic equation. We consider in this work one-dimensional model with two phases that has into account multicomponent float in porous medium. There is several engineering words about this kind of model. The first model study that take into account only one phase. One example is this model that together pseudo present one example for the case that n equal 1. And in this case, the characteristics analysis of this model show one eigenvalue that consists in the derivation of the flow respect to S and n chemical eigenpairs F divided by S. In this case, only the saturation change, and in this case is vary only the chemical compound. One useful simplification in this case occur when the flux not depend of the component Y. In this case, we have a contact wave for this way. This simplification, this result is useful when we try to find the Riemann solution. Also, it's important to consider the case that we have a coincidence of eigenvalues, because in this case the radiations stop. Okay, so in this case is a particular system because in both sides of the coincidence locus we have real eigenvalues, as was studied in this paper. There is another paper that try to study similar problems, and this motivates a generalization. The generalization consists in to consider a system in this way, where the chemical compound appear multiply the saturations, and the Darcy velocity appear only in the flux. So the accumulation not depend on U, and this implies that the Jacobian accumulation has a zero column. We are interested in solve the Riemann problems associated to this system. This system appears in geochemical problem, thermal flow, and we try to show you today all the solutions that, or the structure, what we need to solve the Riemann problem. That since we have n variables, we can we think that the problem is too difficult, but the structure of the accumulation of flux allow us to obtain a simple solution. One particularity is the Jacobian has 0 in the column, and this structure of the product of chemical with saturation and flow allow to obtain a special kind of the eigenvalue matrix. This special kind allowed us to take explicit expressions for the main structures that we need to solve the Riemann problems. Then we have this general solution. The eigenpair consists in the saturation wave that we call Berkeley-Lever eigenpair, because in this way only the saturation change, and we have n composition chemical eigenpair that we associate with the parameter delta, and they have this simple formula. Delta satisfies this eigenvalue, generalized eigenvalue problem, and the vector V also serves to obtain the corresponding eigenvector associated to this eigenvalue. So this is the general structure of the eigenpair. In this case, the matrix A and B only depend of the chemical variables, which we use to obtain more simplification result and reduce the dimensionality of the problem. How do you know the integral curve are obtained from the integration of eigenvectors, in this case for Berkeley-Lever wave, and in this case for the chemical wave. So in the first way it's easy to obtain because it's integration, and we have the Berkeley-Lever rarefactions. But studying the structure of the system, it's possible to obtain the rarefaction only in the projected space of the chemical variables. In the Wanderson thesis, he studied the possibility of draw up in the study the Darcy velocity and to obtain the solution only in the saturation and chemical variable. But in this work, was possible to obtain the new result that also is possible to separate the saturation and obtain the rarefaction only in the chemical variable. For the saturation, we see that it's possible to do in the Rankine-Gounod locus curve also. So this is a useful simplification that allow to construct the sequences of the wave to solve the Riemann problem. Then we now show some general structure of the bifurcation. The notation is no nice, but I try to explain some figures to understand. The inflection curve for saturation has this has expression, and this consists in two surfaces associated to solve this equation. This is important because this structure implies that the saturations, Berkeley-Lever saturation stop in this inflection point. Then the another interesting structure is the coincidence of eigenvalue saturation and the chemical eigenvalue for all E. For this structure, we obtain some useful result that, in summary, imply the following. This geometrical characterization implies that the structure of the coincidence surface are parallel in the projected space, or means that the saturation in air surface or hypersurface vary slow, and we have this structure in the phase states. This is very important because we have several chemical waves together with Bock-Curie lever. Then to find the solution, it's useful to know how is the geometric behavior of the solution. This is the case of three-dimensional case, how look the surface of coincidence of eigenvalue. Now, another interesting structure is when the flux, that in this case we assume that the flux also depends on the chemical variables, is the case that the flux is equal to the variable S. In this case, we have the following results. This is inflation for this is Mailybaev, the inflation for the chemical compounds, and then we have this precision that characterizes the inflection for the chemical wave. In this case, the chemical wave is the sum of C is this surface, and also include the surface of when the eigenvalue Bock-Curie lever is equal to eigenvalues chemical compound, and another curve that only depends of the chemical variable. Another interesting result that is useful also is that in the case that we have delta equal to 0, we have two possible eigenvalues that consists in linearly generated. We have contact wave for this case. So in general, this is the structure of the solution. Note that the hypersurface when the flux is equal to S look in the middle, and another surface the saturation is do not change significantly quick the saturation. So with this result structure in mind, we obtain this another characterization. It's possible to show that there is two invariant regions for rarefaction Augounian locus. So this surface separates the space in two parts. So Riemann problem that start here and end here do not cross this surface. Only is possible to cross this hypersurface with Bock-Curie lever wave. This is useful result also that characterize of the structure of the solution. Rankine-Bonneau correspond to this continuous solution. In this case, the result that I announced is that it's possible to obtain the Riemann solution, the curve in the project space, and the geometric interpretation that the hypersurface CS also is the barrier for the Rankine-Bonneau curve. The strategy to solve the Riemann problem also is the following. We first obtain the Bonneau locus in this project space, and after we obtain in the full space of saturation, chemical space, and Darcy. This is the general idea. Here, well, in the case that the deltas are different, we have a stricted hyperbolic case. One example. In reality, we have two examples that are physical interested. The IGDO and ClickDO model that's modeling the injection of carbon dioxide with water in rock, sandstone rock, and have the same structure. That's the system that we present you. So the idea, well, we first solve these examples and develop the general solution based in previous resolve Dan and Wanderson. In this case, this is consists with the general theory. It's the cure that you remember is only depend of pH. pH in this case is the chemical variable, and another structure has the inflection for the saturation, the inflection for the chemical variables, and then this is the general structure of refraction and shock. And you know, only in this way, in this direction, we can to cross with Bockri-Lever solution. So one example is the following. How do you know? There is several regions to study in this case, and we prepare a Riemann solver, MATLAB, to solve all to implement the wave curve method. And this is an example when the left stay here, then the solution in this case consists in rarefaction, the Bockri-Lever, followed with the rarefaction or chemical rarefaction, a shock. This is the composite of rarefaction and shock, and finally a Bockri-Lever shock, how shown in this figure. In this case, this is the solution that satisfy the admissibility and geometric condition. So this is an example on the we solve the characteristic solution of the general problem. We obtain important structures and prove general resolve of this class of the problem. We exhibit the general shape of integral and shock curve. We obtain useful explicit expression for the more important structure. We show that it's possible to obtain further Riemann solution in the project space of the chemical space, and then we solve in the full space. Well, we show two examples of geochemical interest. Okay. Thank you.
Thank you, Amaury. Some short questions.
Can you show the picture of the example of three-dimensional where we have some...
It's the coincidence locus.
The coincidence goes to the origin, isn't it? The first
This?
this one goes to the origin.
Ah, yes.
Occurs in the case of dimension 2 that I...
Yes, very interesting.
you know how the rule there, if it's tangent to the plane, some plane or?
This is why the following. This sample corresponds one experimental case. That experimental case obtained by Hans with the chemical program frequency. So the parameter of the model, the chemical parameter, has a brute variation of pH close to pH 2.8. So this abrupt variation produce this variation in the surface. In this case, it's for one practical example.
But I guess that this should be something that we always occurs. At least in 2 dimensions is quite stable, that kind of configuration.
But in this case, correspond to different parameters because it's slow, it's always is parallel. But in the case, have a brute chain, produce this chain. Okay.
Do you think that there are situations that would require a model with elliptic regions to model this?
In this case, we do have elliptic region. Only hyperbolic from both sides of.
I guess what I mean is, so many models that people have proposed have elliptic regions. Is that because it's a bad model, or is that because it's modeling something more complicated?
My opinion. Well, I don't have a conclusive opinion, but in general, the hyperbolic system have ill-posed problems. So maybe in the boundary of elliptic region, when the boundary of the coincidence, the behavior of the solution of the generalized eigenvalue is too sensitive to the boundaries. So appear, for example, coincidence or appear elliptic eigenvalues. So I think it's the mathematical nature of the eigenvalue problem produce this behavior in the eigenvalue.
May I comment on that? Is that I have had numerous discussions with people on elliptic regions, and I was 20 years ago influenced by Hans van Duin, who said, "Oh, then there is something wrong with the model." And we had a particular example with polymers, where indeed it turned out that you had to include some other aspect like diffusion in order to avoid it. But I think even Dan disagrees with me here, I think so. I do not dare to say much more about it. Is that the occurrence of elliptic regions means that the models are having a fault in the sense that the way we try to define empirically relative permeabilities is not right in a fundamental sense. And sometimes we can circumvent it, but if we cannot circumvent it, something is wrong with the model. Which I know that many people disagree with this. Very much. Huh?
I agree.
Yeah. Sorry, Gregory.
Okay, thank you very much, Amaury.
Okay.